Hello everybody, Mark Williams here again with another video about wireless networking. And today's topic is fast roaming with opportunistic key caching. Opportunistic key caching is a big subject. Fast roaming is a big subject, complicated subject, and I'm not going to spend a lot of time in this video talking about what OKC actually is and how it works. What I'll do is give you some references so you could research on your own, because if I included all the nitty-gritty about OKC, the video would be 30 minutes long. So a great resource on roaming is a presentation that was put together by this gentleman, David Coleman, and he's on Twitter at Mr. Multipath. And this was a presentation that he gave at this year's CWNP conference in New Orleans. I highly recommend you take a look at this presentation. I'll include the link in the description. Another resource that you could reference for this video is this document from Cisco, which goes into all the details about the fast roaming technology supported on the Cisco wireless platform. We're going to be looking at some of the information from this document as part of this video. So I'll include both of those links in the description of the video. So here's my scenario that we're going to look at with opportunistic key caching is I have two access points, I call them back and front, and I have a wireless client that I'm going to initially associate to the back AP, going to walk up to the front AP, and then back to the back AP. Now, in my earlier videos, you saw me set up a sniffer mode AP on the wireless controller, and in those videos, I was using one AP in sniffer mode. But if you want to test roaming, you're going to need two sniffer mode APs because you can only sniff on one channel. I need to be able to see how the client roams between two APs that are on different channels, so I need two different sniffers. Both of the sniffers are set up to send the packets to the same workstation. Okay, so that's for the setup of the experiment, if you will. Now let's take a look at the data that was captured. So here's what I see in Wireshark, and everything is, my display here is filtered only for packets that are relevant to the roaming and association process. So I've got a filter that's basically just watching association requests, association responses, reassociation request, reassociation response, and EAPOL packets. So I can see when the client's associating, the authentication process and how long that's taking, and also when it roams with the reassociation. So first thing I see is an association request, and this is to the back AP. And from packet 1 all the way back down to packet 29 here is the authentication. So I start with association request and response, and right here begins the EAP process. Then finally down here at packet number 29, I have the end of the four-way handshake, and this is the point in which the client can actually start moving some data. So look at the timestamp here. This whole process took about 200 milliseconds. So that's fairly long. If you're talking about voice over IP applications, having zero data moving for 200 milliseconds is going to be noticeable to a user. So a little bit further down, about 19 seconds into my capture here, I see my first reassociation request. So this is the client roaming from one AP to another. And let's take a look at the details of this packet here. This is a reassociation request, and in it, it says that here's the current AP that I'm associated to, and it's roaming to a different access point. What I want to take a look at here is the RSN information element for this packet. And one of the things that you're going to see here in this reassociation request is a PMK ID count and a PMK ID list. So the PMK ID, or pairwise master key identifier, is information that the client can send to the access point to tell the wireless system that it has a PMK cached, and it can tell the wireless system what PMK it is by sending it the PMK ID. Here's something to note about this. This wireless client had never accessed or associated to the front access point prior to this time. So this PMK ID is manufactured. This is the indicator that this client associates opportunistic key caching because it's giving it a PMK ID when it actually doesn't have a PMK cached for that access point. So here we can see that this client is trying to use opportunistic key caching. At the same time I was capturing the packets with Wireshark and my sniffer mode APs, I was on the wireless controller running a debug on this client. So debug client and then the MAC address of my client. Here at the beginning is the initial association request, where you can see that it's doing the EAP, and pardon my scrolling, we're going to scroll down to the point where it actually finished the DHCP request and is fully authenticated at this point. So we're going to get to the interesting part here. At this timestamp, you see processing association request. This is after the client has roamed to the front AP. And we see in the debug logs that it received an RSN information element with a PMK ID from my client. And this is where it gets interesting. Searching for PMK ID. It's looking for that PMK ID when the client roamed to the front AP. And here we see no valid PMK ID found. So the controller is telling me that client hadn't been on this access point before. So there is no cached key for it. And then the next line, trying to compute a PMK ID. So this is your clue that it's opportunistic key caching. It's computing a PMK ID. And because it's computing it, the client can now roam faster. And it computed a valid PMK ID for the client, and off we go. At this point, we could see that the client didn't actually have to do a full reauthentication. It goes immediately from the reassociation request and response to the four-way handshake. So if I set my reference time in Wireshark by right-clicking on the packet and saying set or unset time reference, you can see from the time of my reassociation request to the end of the four-way handshake only took 37 milliseconds, compared to 200 milliseconds for the full 802.1x authentication. So the key takeaways here are, how do we identify that the client actually supports OKC? Well, we identify it because when it roamed to the front access point, it sent information in the RSN information element. It tried to send a PMK ID, even though the client had not associated to that access point before. And then the debug output from the controller, we see it in the debug logs, it computed a PMK ID for it. Now, if you have a WPA2 Enterprise SSID on a Cisco wireless controller, opportunistic key caching is enabled by default. And there's honestly, from what I could see, no way to disable it. Feel free to correct me in the comments if there is a way to disable it, but I couldn't find one. Then another interesting thing is my client then roams back to the back AP, and you can see, again, by looking at the details of the packet, it's going to send something in the RSN request. Let's see if we could find it. There it is, RSN, and there's the PMK ID. Okay. Now, there's something interesting about this PMK ID. This PMK ID is not calculated because this client had associated to the access point before, and the first one it associated to. And one of the things you can check is at the end, in the first packet, not the end, but the first packet of the four-way handshake, from the initial association, the PMK ID is part of the data that's delivered to the client. So the initial association here, where it went through the full .1x authentication, the first part of the four-way handshake includes the PMK ID from the wireless controller. Now just take a look at the first few and last few bytes of that, 76, B1, 5D37 there. When that client roams back to the back AP, the first one it's associated to, when it reassociates, it's going to send that same PKM ID number. Now at this point, the controller wouldn't have to recalculate a PMK ID for it because the client really did associate to that AP before and should have its key cached. And the client proceeds immediately to the four-way handshake and is authenticated. And just to do this again, I can set my time reference here and see that that four-way handshake and client completes its security association about 35 milliseconds. So that's a quick look at opportunistic key caching. It's supported on the Cisco controller, and the way that you can tell that a client is going to support opportunistic key caching is when it reassociates or tries to send a reassociation request to an AP that it hadn't been connected to before, it's going to send a PKM ID along with that reassociation request. And you'll see in the debug output for that client on the controller that it's going to compute a PMK ID for that client so that it could proceed immediately to the four-way handshake. Anyway, I hope you enjoyed the video. I hope you learned something from it. Give it a like or leave a comment if you see something wrong. And goodbye.